Good evening, everyone. So my name is Anaïs Chanclu, and I am a PhD student at Laboratoire Informatique d'Avignon in France. And I am delighted to present you our article about automatic classification of phonation types in spontaneous speech towards a new workflow for the characterization of speakers' voice quality. So this presentation is divided into 6 main parts. I will first define what voice quality and phonation type are. Then I will describe our proposed system. Afterwards, I will present the data. Next, I will detail the experimental protocol, which will be followed by the results. And finally, I will conclude. So let's start with voice quality and phonation type. So voice quality is considered to have great implication for the characterization of speakers. It can be a permanent component of a speaker's voice due to physiological particularities or the speaker habits. And phonation type is regarded as an articulatory continuum between closed to open glottal state, respectively from creaky to modal, and finally breathy voice. Now that we have defined voice quality and phonation type, I would like to introduce our system using pave as a feature extractor and a multi-layer perceptron for phonation type detection. Very briefly, pave is a variant of autoencoder trained for multitasking. The embedding extractor is optimized to achieve different objectives materialized by a set of workers. For our task, we use the pave plus encoder with the set of workers we consider most useful. And these workers are the waveform, the MFCC, the prosody, the local informax, and the global informax. For the classification part of the system, we built a cascade of 2 binary classifiers. Those classifiers are neural network based, and the first one aims to detect modal and non-modal frames. Non-modal frames are frames labeled either creaky or breathy, and the second classifies classifies the non-modal frames into creaky and breathy type. The neural network classifiers are MLPs composed of 256 node hidden layer, a 015 dropout, and a radio activation function. The output layer is a softmax layer, and the training is done at the frame level during 150 epochs, and with batch sizes of 50 frames. Now I would like to present the data. So the data comes from the PTSVOX corpus, which is a database containing audio recordings in French. It is specifically designed to study the factors of intra-speaker variability in forensic voice comparison. These factors are the gender, the recording equipment, the speaking style, and other information such as the speaker's health state or their smoking habits. For this experiment, all the recordings are resampled to 16 kilohertz. And PTSVOX is composed of 2 sets. The set intra, which contains 24 speakers recorded regularly, and the set inter, which consists in the remaining speakers, which are 245, and they were recorded only once. We will now focus on the set intra. It features 12 female speakers and 12 male speakers, recorded once a month during a 3 months period, using a microphone and a telephone, and they were recorded while speaking and while reading. And for this experiment, we will only focus on the spontaneous speech recorded with a microphone. We specifically focus on the preparsal vowels because they contain linguistic key points since they occur at prosodic prominences, and they are perceptually important in communication. During the annotation process, we isolated vowels directly followed by a pause, and by listening to the vowels and visualizing the spectrogram, a label was assigned to them. The vowels were annotated in 3 categories, breathy, creaky, and modal, and the label other was assigned when the annotation was unsure. As there can be more than one label within a vowel, we use the term segment to refer to the labels within the vowels. And the resulting corpus contains 10,361 segments for 8,889 vowels. I would like now to invite you to focus on the experiment protocol. So I will begin with the reference system. We built a classical MFCC SVM recognizer as a baseline. Acoustic features are composed of 30 MFCC parameters within 0 to 8 kilohertz bandwidth. The window length is 20 milliseconds with an overlap of 10 milliseconds between 2 consecutive windows. We used a support vector machine with the radial basic function for the classifier. Now for the data splitting, we randomly selected for each gender 2 speakers, and we used the corresponding audio data to form a fully separated test set. 20% of the remaining data are then randomly selected to form the validation set, and the rest is dedicated to the training set. The speakers of the test set are never used in the training or in the validation set, and the training and validation set contain recordings spoken by the same speakers. I would like now to present you a table detailing the amount of data for each subset. The models for both approaches are trained on a balanced and randomized amount of data between classes. The predictions are done frame by frame for both tasks, modal, non-modal, and creaky breathy, and both systems with a rate of 100 frames per second. Decisions were made using a simple rule. If the score was higher than 0.5, the recognizer answered yes, and otherwise it answered no. Performance at the segment level was also computed using the mean prediction over all frames before applying the same decision rule. Let's now move on to the results. So if we begin with the modal, non-modal classification, performance is presented using confusion matrices for a clearer visualization of the data imbalance in the test set. At the frame level, 87% of the, I don't know if it's here, 87% of the modal frames and 76%, where is it? Here. 76% of the non-modal frames are classified with the PAVE MLP system. The reference system shows lower performance with respectively 79% here and 72%. As expected, the performance is significantly higher at the segment level, with up to 93% of good classification for modal frames. We also can notice that the performance of the baseline system at the segment level is close to the performance of the PAVE MLP system at the frame level. Now, if we look at the creaky breathy classification, the baseline system has a good recognition rate for breathy frames, with 85% of good classification. It's here, but it shows a clear witness for the creaky frames with only 67% of good recognition. Our PACE MLP approach outperformed the baseline with 85% of good classification for the creaky frames and 88% of good recognition for the breathy frames. This favors the cascade architecture. It seems easier to separate breathy and creaky frames than modal and non-modal frames, although additional experiments are required before a definitive conclusion can be reached. Similar results are observed at the segment level. The performance of our PACE MLP system appears very promising with about 95% of correct classification. And now we are reaching the conclusion. So to summarize, we defined a new neural network solution to automatically detect modal, creaky, and breathy frames on proposal vowels. To do so, we implemented a cascade of 2 binary classifiers based on a representation learning approach for features extraction, which is PACE, and a classical MLP for classification. The proposed solution yielded very satisfactory results, with on average 84% of correctly labeled framed for both classifiers, and the average performance reached 91% when the decision was at the segment level. Our neural network solution PACE MLP clearly outperformed the baseline system, and it also appears to be more stable. So the results opened the door for further investigation. First, the PACE MLP system should be generalized to more contexts and speakers. Our next step is to use transfer learning to pre-train both PACE and MLP modules. And it will allow us to apply the system to all the PTSVOX data as well as on other and larger databases. Second, we will provide expert phoneticians with the best subset of examples for perceptual study and the possibility to integrate their feedback. And finally, we wish to help expert phoneticians to study speaker phenotypes on a large scale, including intra-speaker variability, thanks to the automatic tool we will provide. You will find here the references used in this presentation, and I would like to thank you very much for your attention, and I will be happy to answer any question you may have.
Thank you so much. Do I have to? Okay. So it appears we do have a microphone, so if anyone has questions.
I have a clarification question. Could you explain again the difference between the frame level and the segment level classification?
So the frame level is just one frame corresponds in our experiment to 100th second of a vowel, and the segment is the total number of frames for one label.
Okay, there was another.
Thank you for this presentation. I was wondering if you could elaborate on the telephone condition. Can you predict the results there? So what would it work like if you tried this classifier on the telephone data?
We haven't tried this, but because we only focus on the microphone data, but we can definitely try.
But you have no predictions right now?
No, right now I have no predictions.
Okay, thank you.
Okay. Some other questions?
Thank you for the presentation. So your experiment was evaluated on the data set you collected, right?
Sorry, I didn't understand.
I said your experiment was carried out or evaluated on the data set, the database you collected, the PTSVOX.
Yes.
I was wondering if you probably talked about this during your presentation, but could you please re-explain how that data set was collected and the conditions it was collected in? And then the second one, can you also talk about what do you expect or how do you expect this model would work on just natural spontaneous found data sets that you collect?
So for PTSVOX data, we just asked people to speak in an interview way, and they were recorded once with a telephone and once with a microphone, not at the same time. And same for the reading. And could you please repeat the second part of your question?
I was asking how do you think this model would generalize to any spontaneous data you found? So let's say you ran this model on switchboard or something.
I don't think the model itself, I think it should be just the base of another model to, if you want to generalize the approach with bigger and other databases. Because for now, PTSVOX is only small corpus, and it needs to be completed, so we can have more data.
Okay, any more questions? So I wanted to ask myself, have you experimented with other scoring thresholds? So you had the 0.5. If this would change drastically the results, or
We haven't tried yet.
okay, then thank you so much
Thank you.
for this last presentation.